Okay, so what if I told you that you could build one of the most powerful AI vision systems in the world, not in some giant, super expensive data center, but on a single computer in just a couple of days? Yeah, it sounds like something straight out of sci-fi, right? Well, that's exactly the breakthrough we're going to unpack today. So, a little while back, this new type of AI popped up called a vision transformer, or VIT for short, and it just completely changed the game. See, it was inspired by these models that got really, really good at understanding human language. And the idea was, hey, what if we could get an AI to see an image by paying attention to the important parts? Kind of like how our own eyes work. And guess what? It worked. These things were incredibly powerful, just shattering old records for image recognition. But, and you knew there was a but coming, right? This incredible new power came with a massive catch. A huge catch. To get this good, these models had let's call it a voracious appetite. They needed to be fed an absolutely colossal amount of data. And when I say colossal, I mean a scale it's almost hard to wrap your head around. 300 million. That's the number. 300 million images. That's what the original vision transformers needed to be pre-trained on just to get to their peak performance. And here's the kicker. This wasn't just some random collection of photos you could download. Nope. This was a massive private dataset called JFT300M, which basically meant it was completely off limits to, almost everyone. And right there, you've got a huge problem for the entire field of AI. I mean, if the only way to build the best models is to have these gigantic private data sets and the supercomputers to process them, then all that cutting-edge research gets locked behind the doors of a few giant tech companies. It's like only the biggest players get to be on the field and everyone else is stuck in the bleachers. But this is where the story gets really good. A team of researchers from Facebook AI and Sorbonne University basically looked at this problem and asked a super simple but brilliant question. What if we could get that same amazing performance, but without the absolutely insane data requirements? And their answer was a model they called DEIT. That stands for the Data Efficient Image Transformer. And just look at the difference here. It's night and day. The old way, with the original VEET, you needed that private 300 million image dataset. The new way, with DeiT, they trained it only on the public ImageNet dataset, something anyone can access. And get this, instead of needing a whole server farm, they did it on a single computer in about 2 to 3 days. This wasn't just a little step forward. This was a complete game changer. Okay, so the big question, right? How in the world did they pull that off? How do you squeeze that much performance out of so much less data? Well, the secret wasn't about working harder. It was about working smarter. And the key was to give their model a teacher. The technique is called knowledge distillation. And the core idea is actually super intuitive. You take a big, powerful, already trained teacher model. Then you create your new, smaller student model. And the student doesn't just learn from the answer key, the correct labels. It also tries to copy how the teacher thinks. It's like, instead of just reading a textbook to learn calculus, you get to learn directly from a master professor who explains their reasoning. You learn the why, not just the what. But the DIT team didn't just stop there. They added their own clever twist, something specifically designed for transformers. They introduced a brand new component to this whole process, something called a distillation token. And this was the real secret sauce. All right, let's break down how this little magic token actually works. So in a normal vision transformer, you've got this thing called a class token. Its one and only job is to look at all the pieces of an image and predict the right label, like cat or dog. But what the DAIT model does is it adds a second special token, the distillation token. And its job is totally different. Its goal is to match whatever the expert teacher model is predicting. And here's the really cool part. Both of these tokens are in there together, learning at the same time, sharing information through the transformer's attention mechanism. It's exactly like having two students working together. One is focused on acing the test based on the textbook, and the other is trying to perfectly copy the professor's own answers. By collaborating, they both end up smarter. So this leads to a really interesting question, right? If you're a student transformer, who's the best possible teacher you could have? You'd probably think it would be another, even bigger, more powerful transformer. Learn from the best of your kind. But what the researchers found was something nobody really expected. It turns out the best teacher was its old rival, the convolutional neural network, or convolute. Yeah, a completely different type of AI architecture. See, by learning from a convolute, the transformer could absorb some of its built-in knowledge about how images are structured, what we call inductive biases.
It's like a student who's great at painting abstract art suddenly getting lessons from a master of photorealism. That different perspective, that different way of seeing the world, made the student unbelievably strong.
Okay, so the theory is super cool, but the real question is, does it actually work? Did all this cleverness pay off? Let's look at the proof. This chart pretty much says it all. If you look at the baseline model with no distillation at all, it's already doing pretty well, 81.8% accuracy. Not bad. Now, add in a more standard kind of distillation, and you get a nice bump up to 83%. But look what happens when they use their special distillation token. It pushes the accuracy up again to 83.4%. Now, that might not sound like a huge leap, but in the world of top-tier AI models, every single fraction of a percent is a massive victory. This just proves their new method was the clear winner. And now for the main event. This is DeiT versus the heavyweights. And just look at these results. The distilled DeiT model hits an incredible 85.2% accuracy. Now, let's put that in perspective. That is better than EfficientNet, which was one of the absolute best convnets at the time. And here's the real jaw-dropper. It's also better than the original vision transformer. You know, the one that needed 300 million private images to train. DeiT beat it, using only public data. That is the definition of working smarter, not harder. So, look, the really big takeaway here isn't just that they built a slightly better model. The truly revolutionary part is how they did it. And the implications of this data-efficient approach, well, they're massive for the entire future of AI. First off, this completely helps to democratize AI. It takes that cutting-edge power that was locked away inside giant tech labs and puts it into the hands of more people. It means researchers at a university or even a small startup can now train and experiment with state-of-the-art vision models. It makes the whole field more accessible, way more efficient. We're talking less time, less money, less energy, and maybe most exciting, it opens up this whole new frontier where different AI architectures aren't just competing, but actually teaching and learning from each other. What this research really proves is that the future of AI isn't just a brute force race for more data and more computing power. Sometimes the biggest leaps come from finding a cleverer, more efficient way to learn. And that leaves us with a really big question to think about. If we've just figured out how to teach an AI to see this effectively, what's the next big lesson it needs to learn?